Good morning, everyone, and welcome. I'm Sue Ko, a proud graduate of the class of 1973 with a bachelor's degree in course 18, mathematics. It is an honor to serve as the chair of MIT's Cardinal and Gray Society. My husband Victor and I are delighted to welcome you to today's online lecture. Victor is also a member of the Cardinal and Gray Society, earning his bachelor's degree in Course 6, Electrical Engineering and Computer Science in 1972, and a master's and doctoral degree in 73 and 81, respectively. Thank you all for joining us. Every time I take part in the Cardinal Gray event, whether in person or online, I'm reminded of how our shared curiosity and commitment to Mons and Manas make this a community truly special. Though our journeys have taken us in different directions, the meaningful experiences and lasting memories we share from our time at MIT unite us in a profound way. On behalf of MIT and its Alumni Association, I want to thank you for continuing to honor these connections and for contributing to the enduring mission of building a better world together. It is my great pleasure to introduce Associate Professor Richard Linares. Richard is the Rockwell International Career Development Professor in the Department of Aeronautics and Astronautics and the director of MIT's Astrodynamics, Space, Robotics, and Control Lab, also known as ARCLab. His research focuses on astrodynamics, estimation and controls, satellite guidance and navigation, space situational awareness, and space traffic management. Before joining MIT, Richard served as a director's postdoctoral fellow at Los Alamos National Lab and held a postdoctoral appointment at the U.S. Naval Observatory. Today, he will discuss how the rapid expansion of low Earth orbit satellites is reshaping space operations and what it means for the future of space sustainability. Please join me in welcoming Professor Richard Linares as we delve into sustainability in space.
Thank you for that introduction. So let me share the slides here. All right, well, welcome everyone. So happy to have so many folks here for this talk. I love to share some of the work that we're doing on orbital carrying capacity and space sustainability. And so with that, I want to first start off by discussing my research group and the work that we do at MIT. Our research really spans these four areas. And so we do a lot of work on space sustainability and space weather. So in space sustainability, we want to understand what level of activity in space is sustainable and what levels of activity are not sustainable and things that we can do to make operations more sustainable. We also do a lot of research in space weather. And in the space weather topic, if you remember from last May, we had a major storm that we saw the Aurora Borealis in the Boston area and across a lot of parts of the United States, where those solar storms actually affect satellites as well. And they affect satellites in many ways. And my research group really tries to study what space weather and solar storm, what effect that has on satellites. We also work on space traffic management. In our space traffic management research thrust, we really want to understand how large satellite constellations and future space traffic can coordinate in a way that's safer for on-orbit activities. Finally, we do a lot of work in what we call space situational awareness and computational astrodynamics. Space situational awareness is really a topic coming out of the Department of Defense, where really what we want to understand is what are the distribution of objects on orbit, what are their locations, and can we maintain a catalog of those objects for applications that really span all the things that I'm discussing here. In addition to that, we do computational astrodynamics. And what this is really basic research into the studying of motion of satellites. How do satellites move in low Earth orbit? What dynamical principles can we apply to predict the motion of satellites in low Earth orbit? And developing new algorithms to do that. Here's a photo of my group on the left. Right now, we have about 7 graduate students and 4 postdocs in the group, and you'll see a lot of the work from these folks in the presentation. So let's start off with a motivation of why we're studying this problem. And the issue is that there needs to be more coordination in the design of orbits between these large satellite constellations. So if you've tracked what's going on in space, one of the big trends currently is that we are seeing satellites being deployed in very large constellations. Now, a constellation of satellites is just a large number of satellites that are operating in unison to achieve a goal. In this case, this increase in large satellite constellations that we're seeing is mostly for broadband applications. So you've heard of, hopefully, Starlink. Starlink is a very large constellation of broadband satellites run by SpaceX. If you've heard of other satellite broadband applications such as Viasat and Inmarsat and other constellations like that, Viasat is used by airplanes. When traveling across the continental United States, you can, on your flight, connect to the internet. That connectivity is provided by those satellites. And Starlink and many other satellites are providing similar services. Now, we need very dense constellations so that we can cover the entire surface of the Earth in terms of internet connectivity. And that's why the numbers of satellites grows and it becomes really large, these constellations. Now, there's a couple of trends that you could see. For example, if you go lower to the Earth's surface, then the satellites don't have a lot of footprint on the Earth's surface. So, for example, if you get very low, the potential sites where the satellite is above the horizon, that footprint gets smaller because the satellite gets lower. So you can think about, for example, a cell phone tower. If the tower is taller, it can cover more area. So as you get higher in altitude, a single satellite can cover more area. But the issue there is the distance to the ground increases. So the path lengths, your communication path lengths get longer. So the speed at which you can connect is slower. So there is a driver to get closer to the ground, which also drives increasing the number of satellites in the constellation. This simulation is showing proposed constellations. Some of these have already been deployed. Some of these are still in planning. For example, SpaceX has about 5,000 satellites on orbit right now. OneWeb has close to 1,000 satellites on orbit. Viasat has many as well. And there are more constellations that are being deployed. And then that view contrasts this with what we've heard, that there's a space debris problem. So Hollywood's take on the space debris problem is the movie Gravity. Of course, it's a bit of an exaggeration of the space debris problem. In particular, like if you watch this clip, some of the physics here is exaggerated for dramatic effect. But the issue is on the public's mind that we know that there is a lot of debris in low Earth orbit and we're increasing the traffic. What does that mean for the debris population? You might ask, where does all of this debris come from? Well, a lot of the debris comes from mission-related debris. So different space missions during their normal operation might jettison parts of the satellite and create space debris. That might sound like, wow, in today's world, that seems kind of irresponsible. But back in the days of early space flight, space was assumed to be big. So doing this kind of activity was not seen as being detrimental as much as we see that today. But nowadays, we have new practices that will hopefully reduce the number of debris that's generated, mission-related debris. But in the end, we can't reduce that number to zero because satellites, like any other engineered system, have a non-zero probability that they might fail. So just like when we buy laptops or cell phones, our cell phones have a certain lifetime that we expect to use them for, maybe 2 years, but there's a non-zero probability that could fail before that. If a satellite fails on orbit before its lifetime is over, there's not an opportunity to deorbit that satellite and remove it from space. And it becomes a derelict satellite on orbit, which is basically a piece of debris, just a very large piece of debris. And that satellite could potentially collide with other satellites. And then this collision effect is what's known as the Kessler effect. And the Kessler effect is that the density in low Earth orbit might get high enough that each collision generating debris would increase the probability of future collisions. So it's really this cascade effect that is as the density reaches this critical threshold, we could have a cascade of multiple generations of collision, increasing the number of debris. So that's one of the issues that we want to avoid. And some folks have said that this could potentially render space activity unfeasible for many generations. And you might ask, why would it be unfeasible for so long? Well, low Earth orbit has a natural cleaning effect. And that cleaning effect in low Earth orbit comes from our atmosphere. And if you've dealt with any kind of fluid, we know that the pressure of, for example, let's say the ocean, the pressure of the ocean varies with the height of the water. So as we get deeper and deeper in the ocean, the pressure increases. In space, we have the same effect, right? So as we get closer and closer to the Earth, the pressure or the density of our atmosphere increases. But the opposite effect is true. As we get further away from the Earth's surface, the density of our atmosphere gets very, very low. And that means that the cleansing effect of the atmosphere is no longer there. The atmosphere applies a drag on satellites that removes satellites and space debris. But as we get higher in altitude, that reduces significantly. And above 1,000 kilometers, it gets very low. So the issue with space debris is if we generate a lot of it, it can be up there, depending on the altitude, for thousands of years, if not hundreds of thousands of years. And it's very hard to remove. So we want to do things before it's too late. And so we've seen in the recent past that governments are concerned about space sustainability, going from NASA to federal agencies here in the US, such as the FCC, which regulates communications and regulates communication satellites, to ESA in the UK. A lot of initiatives have been proposed to really tamp down the space debris issue. And NASA released their space sustainability strategy, where they're really going to focus on ways where they can encourage folks to operate in more sustainable ways. FCC has fined for the first time a company for a space debris event. The Dish Network satellites had a failure that caused a debris event, and they were fined $150,000. It's not a lot, but it's really the signaling that, you know, we're serious about space debris and we want to be careful and reduce future space debris. ESA has a zero debris charter. The issue that we see from our work at MIT is that the governments do want to do something before it's too late. But in a lot of cases, there aren't any hard numbers and physics behind these initiatives. So a lot of these initiatives are really, we know that this will be positive, for example, to fine companies for space debris events. But what we argue is we really should model this stuff physically and understand which policy levers have the greatest effect on the end goal, which is to reduce our space debris population. And at MIT, we developed something that's called MOCAT. MOCAT is our MIT Orbital Capacity tool. And we hope to change that with MOCAT. And I'm going to describe MOCAT in this presentation. But MOCAT is really a tool that we open source to the community and can model a lot of these issues that these governments are trying to affect. And so we've open sourced this tool. We announced the tool more than a year ago now at the OECD Space Forum in Paris. And the tool, the reason we open sourced the tool, announced it, is when you look at the space debris research world, there are various modeling approaches out there. Some of these approaches are coming from the major space agencies. But the issue with these modeling approaches is that they tend to be closed source, and their results are difficult to replicate. In the end, what this is going to lead to is a muddled debate amongst experts in the field and policymakers. And what we hope to do with MOCAT and our work at MIT is provide an open source tool that anyone can access. And you can look at all of the assumptions in the tool. And at the end of the day, what we hope this tool is just the physics of the problem, right? So if we can agree on the physics of the problem, hopefully we can understand how to promote the economic activity that we want to have in space, but do it in a more sustainable way. And if anyone's interested, here are some GitHub links that you can download MOCAT and use it yourself. And so before I get into the body of the presentation, I did want to introduce some basic astrodynamics. So I wanted to introduce orbits. So for example, we have parameters when we study orbits. The first parameter, let me start that video again. The first parameter we consider is the semi-major axis. You can see it in this video. The semi-major axis is really the size of the orbit. If you've worked with the geometry of ellipses, The semi-major axis is really the long axis of the ellipse. And orbits are elliptical in shape. So that's the first parameter, the semi-major axis. The next parameter is eccentricity. That governs the shape of the orbit, how eccentric the orbit is. And you can see the eccentricity is being swept here. The orbit's becoming more eccentric. There's a close approach point, which is called the perigee, and the furthest point, which is called the apogee for Earth orbits. And then we sweep through these parameters and we look at the next one, which is the inclination of the orbit. Now, these communication satellites require inclined orbits, and the reason they do that is they really want to get a latitude spread. So they want to cover multiple latitudes, and we can do that with inclination. The next orbital parameter is the right ascension of the ascending node. Now, this is really the orbital plane's, think about this as the orbital plane's yaw angle. So we're computing a yaw angle, but an orientation of the orbital plane. And this is critical for these large constellations because this allows the constellation to be spread across the globe by changing right ascension to ascending node. Additional parameter is the argument of perigee, and you want to think about this as where is the close approach point and how are we varying that. And finally, the true anomaly angle is the angle along the orbit. So I did want to introduce these because I will bring up some of these values later. And when I talk about the altitude, I'm really talking about the distance from the orbit to the Earth's surface. That is the altitude of the satellite. Okay, so let's get bottom line up front. So I'm going to talk about some of these simulations here. And so we have two simulations that I'm showing you here of MOCAT. And what I'm doing in these simulations is we're simulating the future evolution of the space environment. On the left is an evolution where there's no future traffic. We've stopped launching satellites today. Actually, the simulation started, I believe, 2023, but we stopped launching satellites and we want to know what the evolution is of the space environment. In green, you see active satellites are in green, and red are debris. You see this initial green? This initial green is, we stopped launching today, but there's still some satellites up there. But you can see that a lot of the satellites very quickly deorbit. A lot of the satellites are in lower orbits, so they're affected by the atmosphere, so they will deorbit fairly quickly. But what stays up there is the debris that's in higher orbits. And this debris continues to collide with other pieces of debris, and you can see that simulation becomes more red as we see an increase in debris. Now, if we simulate with our tools the future traffic, the simulation is much more dramatic than the left. The future traffic, we anticipate about 80,000 payloads are going to be launched to low Earth orbit. In that simulation I showed earlier, you can see that this very sharp increase in green. Now that's this dramatic increase in the number of satellites that are going to be launched. And we've already seen that. SpaceX has more than doubled the number of satellites in low Earth orbit. Low Earth orbit is usually from 1,000-kilometer altitude up to 2,000-kilometer altitude. Those are the ranges for low Earth orbit. And Starlink has more than doubled this number. And then what we see is that it becomes very green initially, but then there's this large increase in the debris population. We're going to dive into these numbers in the presentation, and we're going to really want to know where is this extra debris coming from. I will caveat these two simulations by saying that the size of satellites are not shown to scale. Of course, these are pixels, individual pixels for the objects, and satellites, if I were going to show them in this scale, they wouldn't necessarily be visible, right? So space is still big, but the numbers, I think, are accurately reflected by these two simulations. All right, so now when we talk about the issue with the increase in debris, what we want to understand is what capacity do we have in low Earth orbit to launch satellites? And what we mean by capacity can mean many different things. But one definition of capacity is sustainable capacity. We want to live in a future where the space debris population is not out of control. So we'd like to study, and this is something I do in my group, at what level does the space debris population grow? And can we stay below that level? And can we define a capacity that is sustainable? Now, this is a multifaceted question, orbital capacity. And it's governed by many things. So it's not just governed by space debris. It's governed by issues of spectrum. So these broadband constellations in low Earth orbit are communicating in electromagnetic radiation. And this spectrum, electromagnetic spectrum, they occupy parts of that spectrum. So in a lot of cases, you don't want to interfere with other satellites by broadcasting in similar spectrum bands. So this is something the FCC takes care of and regulators take care of licensing who can broadcast in different spectrums and keeping spectra for public use as well. And so that's limited. So we can't launch an infinite number of broadband constellations because spectrum becomes an issue. Light pollution is also an issue. You might have heard about this with Starlink, that, if you look up at the night sky, in a lot of cases, you will see a lot of Starlink. You typically see them around dawn and dusk. And the reason you see them around dawn and dusk is because the Earth's shadow is at an angle at these dawn and dusk periods. So the satellites are not in the Earth's shadow, right? But when we get in the middle of the night, the satellites are in Earth shadow, so they don't reflect as much light because they're in the Earth shadow. This light pollution affects astronomy. We also have emissions issues when the satellites deorbit and re-enter our atmosphere. They're mostly made out of aluminum, so they will deposit aluminum in our atmosphere. So our atmosphere will essentially disintegrate the satellites as they're re-entering. The satellites are traveling very fast, hypersonic speeds. So the heats that are involved in that friction of re-entry will cause the materials to break up, but that material goes somewhere, and some of them can go into our atmosphere. So this deorbiting effect could reduce our capacity. There's also an issue of orbit volume. How much volume is the satellite taking up in space? And it could be physical volume. You can think about the size of the satellite, solar panels. How much of it is it taking up in space? But there's more than that. There's the uncertainty in our estimate of the satellite's position. And there's also the uncertainty in the satellite's ability to control its own position. And so you can really think about those two things coming together and defining an effective volume that the satellite occupies. Finally, there's operational collision avoidance constraints. So if you have a lot of debris and a lot of satellites, they're all going to want to avoid collisions with each other. And we might get to a level where these collision avoidance maneuvers overwhelm our current systems. And this is an issue as well that I brought up earlier, the long-term sustainability issue, which is central to the discussion I mentioned earlier on our environment. So our work at ARCLab, of course, there's many different factors that bind orbital capacity, but our work is really just focused on these three. There's some folks at MIT that are focused on the other three. In particular, Dan Hastings in our group does a lot of work at admissions. We have visiting faculty member Mariba Jha from University of Texas, Austin, has done a lot of work on light pollution. And Ed Crawley from our department as well has done a lot of work on spectrum. So the research that's happening at MIT really covers all these bases, but ARCLab in particular, we focus on these three here. Now, when we do those three topics, we really want to think about them in two separate ways. There's the topic that we call, this is our term, intrinsic capacity. And then there's a topic that we call risk-based capacity. Intrinsic capacity is, you want to think about this as an ideal setting. Let's assume that we have no space debris and we want to operate many operational satellites. How many operational satellites can we configure in low Earth orbit in this very ideal setting? And if each satellite has a keep out region, orbit volume that it's occupying, this intrinsic capacity calculation, which we've done a lot of work on, is very much related to the sphere packing problem in mathematics. If you've ever heard of the sphere packing problem in mathematics, it's really this idea of like, how many spheres can I fit in a fixed volume? And it's a classic problem in mathematics. So really this intrinsic capacity for satellites is a generalization of that. So think about the sphere packing problem in a dynamic environment. And that dynamic environment is governed by Kepler's laws of motion and Newton's laws of motion, in that these spheres are moving and they're not stationary, but they occupy a certain volume in the phase space, the space of all possible orbits. They occupy a volume. What we want to do is we want to understand how many of these orbits can we fit in low Earth orbit. And we call that the orbit packing problem. So we've done a lot of work on this. I'm not going to cover that too much, very mathematical topic, but I won't cover that too much in this talk. What I will cover in this talk is the topic on the right, which is the risk-based capacity. Now that we understand how many orbits we can pack, the question is, well, each one of those satellites has a non-zero probability of generating debris. And the debris that's generated from those satellites will actually reduce the capacity in its local region, because if there's debris occupying volume, active satellites have to avoid that debris. we call this risk-based capacity because it can't be done in a deterministic fashion. It really has to be done probabilistically. One, because we don't know what the future debris orbital states are going to be exactly, right? Those are going to evolve as we have random failures occurring and as we have collisions occurring. So it really needs to happen in a probabilistic way. So our group at MIT has really led the development of these two complementary ways of thinking about orbital capacity. Now, I want to describe the risk-based capacity calculation, and there is a bit of mathematics here, but it's very simple. So hopefully most folks can follow along. And so essentially what's going on here is we try to describe the space debris population in various ways. One of the simplest models for doing that is called the source sink model. Now, if you've ever dealt with epidemiological models, such as the models that we used during COVID to model disease infected and recovered individuals, so we could understand the load on our medical infrastructure, these source sink models are very much like that. They model the population in terms of buckets. Think about classes of objects. So we might have intact objects, we might have debris objects, we might have rocket bodies, we might have various types of debris. And in this diagram, I'm showing you the simplest case where we have two classes, intact objects and debris objects. And a source sink model really models the sources and sinks of both classes. For example, what are the sources of intact objects? Well, intact objects are satellites that we launch into orbit. And so a source is launching new satellites into orbit. Another source is potentially, if we're looking at a single orbital shell, we might have intact objects in shells above us, so altitudes above us. And they're going to naturally decay in their altitude due to atmospheric drag and friction. So because of that friction, intact objects will lower their altitude and enter into this shell that I'm showing here. Another source, a potential sink is as well as decaying from altitudes above, they could decay to altitudes below and potentially deorbit. So that's a removal of intact objects from the population. But intact objects can also transition from intact objects to debris due to collisions. So if two intact objects collide, they'll produce debris, quite a lot of debris. And debris has the same effect as intact objects. They can decay from higher altitudes, and also they can decay into lower altitudes. So that's a source and potentially a sink. If you boil down these equations into the simplest mathematical form that we can write, it's actually a ordinary differential equation of polynomial form. And it looks like this. And we can actually describe most of the terms in this equation. So for example, launch, think about launch as a constant term. We're launching satellites, and it's not a function of the number of satellites that are up there. It's really a function of our demand, how many satellites we'd like to launch. The decay can be modeled with a coefficient times the number of objects. And so this is how we can model atmospheric decay. And collisions, since it's a collision between two objects, it can be modeled as an n squared term, right? Because the number of potential collisions that could occur, number of pairs between two objects, is n squared, times a coefficient, which governs if we have a collision, how many debris is generated. Let's say one collision will generate 100 pieces of debris, and that's that coefficient. If we boil down this equation, we can see that this equation is actually zero at two roots. It's a second order quadratic equation. If I set it equal to 0 on the left, I can have two roots of this equation. So you want to think about setting this equal to 0 are the equilibrium solutions. So what environmental conditions could potentially lead to equilibria? We want to know that because those are sustainable environments. And equilibria tend to happen when the number of collisions balances out the cleansing effect of the atmosphere. So we reach this equilibrium when these terms all balance. And one of the things we can do is we can look at what these equilibrium solutions look like as we vary the launch rate. And as we vary the launch rate, you can see that we have actually two equilibria. One of the equilibria is stable, the other equilibria is unstable. And if you look at the equations, it's very easy to see how you could generate two equilibria, right? There's two roots of this quadratic equation. And you could also see why you have an unstable and stable root. So you can see that from the equations. At a certain launch rate, these two equilibria actually converge and become imaginary, and there aren't any equilibrium after that launch rate. This launch rate is what we saw earlier. It's the Kessler syndrome. But it turns out there are a lot of launch rates that are not Kessler, and you can see these launch rates will result in equilibria and populations that are stable. So what we want to understand is, what are these potential configurations look like, and we want to study them so that we can see whether or not our environment could be in these potential configurations. And this is how we study these source sink models. Of course, the analysis here is very simple. What we do is a little bit more complicated, but I think this captures the essence of what we're doing with source sink models. And then on the Monte Carlo front, we're taking a different approach. So instead of modeling objects in these very generic buckets, what we do on the Monte Carlo front is we model objects individually. Each individual object is simulated with high fidelity models, and we model the characteristics of that object. We might model the size of the object, the mass of the object, the ballistic coefficient, which is the ballistic coefficient, you want to think about that as similar to the drag coefficient of an object. How much drag does this object experience? And in that, we can basically predict forward where that object's going to be and model all potential future collisions that object might have. Of course, some of those collisions are uncertain, so we don't model one simulation of the future. What we really want to do is model a Monte Carlo of simulations of the future. Monte Carlo is this term from statistics, and it goes back to the casino in Monte Carlo and gambling. But really what Monte Carlo is randomly sampling in a computer using random number generators, potential realizations of a random variable, and then simulating that forward to see what the outcomes are. So we could do this with the future population, and we get many potential futures. And what we want to look at is the spread of these futures and then the mean of these futures. What's the mean value and how much is it spread? And what I'm showing you here on the left is active satellites. So active satellites are going to be in these well-behaved orbits, but we also have debris. And I'll show you a video of the debris in a second. They're not going to be in these well-behaved orbits. They're going to be spread and spread more randomly. And the spread is going to be due to the collisions that occur. So on the left, we have the source sink model that I showed you how you could generate equilibria with. And on the right, we have the Monte Carlo model. Of course, the source sink model, it's very simplified. So the results of that, they're not as accurate. But the Monte Carlo model, most major space agencies, this is what they use. This is what we use when we study orbital sustainability. We use Monte Carlo models. One thing that we've done in my group is really bring up the fidelity of the source sink modeling, and we've made the source sink models much more credible. Now these source sink models can be used in policy level optimization. So what you can do nowadays with the research that we've done is you can do trade studies. What if we enact this new policy that active satellites have to deorbit in 5 years? Does that really have a measurable effect on the population? So that's work that we've done to increase the fidelity of source sink models. But then what we've also done is, once you have a result in the source sink model, you can reproduce that result in the Monte Carlo model and see whether or not this is a real environment. So the source sink models, big buckets of objects, what we can do is we can translate that and have a specific object for every number in that source sink model. So if you look at this graph here, active satellites, you see it's 10 to the 4, a few thousand, but we can generate a few thousand active satellites in the same distribution as a source sink model and verify that we get the same result. And one of the things that we've done in our group is we've shown through proper modeling, you can do that. You can generate a policy level optimization in a source sink model and reproduce that in a Monte Carlo model. And this is what some of those policy level optimizations look like. So for example, what we're optimizing here is the orbital capacity. So what we've done is we set up a optimization metric in the source sink model where we want to maximize the number of satellites in each orbital shell. And you see each one of these dots is the number of satellites in that shell. You can see there's many orbital shells. We want to maximize the number of satellites in each orbital shell subject to a failure constraint. So as I said earlier, we can generate a lot of equilibria. Not all equilibria are equal. But what we want to be able to do in this simulation is have a very specific condition for the equilibria. that only a certain percentage of satellites fail due to debris on satellite collisions. So for example, in this simulation, we had up to 7% failure rate. So 7% of active satellites are colliding with a piece of debris and potentially failing due to that collision. And what we're showing you here is the maximum capacity under those conditions versus what's in orange is what the future FCC traffic looks like. We can see in most altitudes, we're below that capacity. Some altitudes we're not. And that's because there are these Goldilocks zones in terms of economic value on orbit, where a lot of constellations want to go there. One, because it balances this effect that I mentioned earlier. If you go too low, you need a lot of satellites so that you're over the horizon. If you go too high, your link budgets don't work out. What I mean by link budgets is the amount of data that you can transfer over your network is not as high for an economically viable constellation. So there are these really nice zones, and it turns out that one of them is right here around 690 kilometer altitude. Starlink has a shell there, Amazon has a shell there, and China's new broadband constellation, they have a shell there. And then one of the results of our work is, okay, so we have these issues that there's these high demand regions. What can we do about it? It turns out that orbital capacity is not this one answer monolithic number, but reality, it's like a balloon that you can squeeze. So you, for example, might have your global optimal condition, which is showing this global optimal in blue. This is the optimal capacity, these blue bars. But then you might have owner-operators of satellites projecting their demand. And if you look at your demand model, you might have higher demand in this region than the capacity allows for. It turns out that you can accommodate that in a sustainable way. And the way you do that is you have to reduce the capacity in the shell below. The orange bar is the accommodated solution. You reduce the capacity in the shell below it, and you reduce the capacity in the shell above it. So it's really like this balloon where you squeeze the balloon on two ends, and then you can puff up the balloon in the shell that you want. And why is that the case? Why do I need to reduce the capacity in the shell below and above? Well, when we talk about these equilibria solutions, they're these perfectly balanced solutions of debris generation and debris cleansing from the atmosphere. So if this is a balanced solution, basically the rates of debris generation are such that everything balances out. If I add more satellites in this shell, that means that I'm generating more debris than the optimal solution. That means that the debris that I generate is going to rain down on the shell below, reducing the capacity in that shell below. If I have more satellites in this shell, I can't accommodate as much debris from the shell above. So the debris that this shell is generating, which is raining down here, has to be lowered. So that's why we need to squeeze the capacity in these two regions. So it's very nuanced, but the good news is, it's not, there's not a single answer to this. I think there's a lot of room for us to generate really good economic activity in low Earth orbit and realize the future that a lot of us have dreamt of, where we have a space economy, but we can do it in reasonable ways where we're not increasing the risk of space debris. And one of the plots that I like to discuss is really just showing that this orbital capacity is not a single number. In reality, it's a manifold. And what we like to call it is the capacity risk manifold. What I'm showing you here is the optimal capacity across all of LEO, all low Earth orbits, as a function of failure rates. We've talked to many owner operators, and they tell us that the failure rates that they want to see, this is 1%, are below 1%. So these failure rates up here are not good in terms of what they would like to see. So this is too risky. But the point to take away here is that we actually can generate many equilibrium solutions. It's a question of how much risk do you want to take in low Earth orbit of potentially failing due to debris collision. But these solutions are also they're also generating a lot of debris, but they're also generating a lot of that debris at lower altitudes. So these debris are not being generated at higher altitudes. So it's really very high capacity, but it's at lower altitudes. Now, going back to the Monte Carlo modeling, every major space agency has their own model. So NASA has a model called Legend, ESA has a model called Delta. But the issue with all of these models is they're closed source. A lot of these models use semi-analytic orbit propagation and use similar tools in the way that they calculate. And they've released that in publications, but the actual assumptions and the code of the models are not, you can't interrogate them. If there's a result that comes out of it, it's not as transparent. And that's really one initiative that we wanted to do with our work at MIT, which is completely in the open and transparent. Anyone can take our model. We're under an MIT license, can improve on it and do great things with it. But the benefit of our model, as opposed to some of these existing models, is we've been really able to push the envelope of the state of the art. So if you look at what these models are able to do in terms of the maximum populations that they can model, they're limited around, let's say, conservatively 500,000 objects in their simulation. But we've seen from the discussion earlier is that we might have up to 80,000 active satellites in future environments. And with 80,000 active satellites, the amount of debris that's going to be generated is well above 500,000. And so one of the things we were able to do with our work at MIT is really push the state-of-the-art envelope. We can simulate many millions of objects, tens of millions of objects. And we're able to do that through some innovation. We've innovated really on the orbit propagator, choosing to go, instead of a semi-analytic propagator, a fully analytic propagator that's adjusted to match the evolution of the distribution of the population. And also we use significant high performance computing resources at MIT. So this is really what we're modeling. We're modeling the Monte Carlo model. These two objects I'm showing you here are about to collide. When they collide, we use the NASA standard breakup model to model how the debris is generated from that collision. As you can see, due to that collision, the debris is generated in the orbital planes of the original two objects, but the debris is also spread. It's not only in that original orbit, it can have eccentricities, so it's also spread in the eccentricity. Going back to what I discussed earlier, in terms of the orbital parameters, what you're seeing here is that the original objects had two different orbital planes, and now the debris resides in both of those orbital planes. Now, if we look at the long-term evolution of that debris due to that collision, we can see that at the original altitude where the objects were, that's where the collision happened. But what I'm showing you here is something that's called the Gabbert plot. What I'm showing you here is the altitude of the perigee of the orbit and the altitude of the apogee of the orbit. So I mentioned that earlier. The perigee is the close approach distance. The apogee is the furthest distance. So I'm showing you both points in one plot. So I'm plotting those two altitudes along with the orbital period. So the orbital period is going to be the same for those two altitudes. But what you can clearly see is when the collision happens, we have points that have a perigee at this value and an apogee at that value here. So they're not circular. The perigee and apogee are not the same. So they have some eccentricity. So really what's happening is that collision happened at this altitude, but it kicked up debris at these higher altitudes. So that's kind of an effect that we want to understand. If we're kicking up debris into higher altitudes, they're going to be up there for quite a bit of time because the density is quite low at these altitudes. We might have some objects that have high area to mass ratio. So you could see we've also plotted the size of the objects. So some of these objects that get kicked up are smaller. And the fact that they're smaller, they tend to have higher area to mass ratio. So think about a piece of paper having a high area to mass ratio as opposed to a dense textbook. So that piece of paper is going to be pushed around by a wind where the textbook won't be. So if there's drag in the atmosphere, it's going to push that piece of paper much more than a dense textbook. And so these lighter objects tend to deorbit quicker, but some of these heavier objects can stay up there quite a bit of time. And you can see the ones that are lower in altitude deorbit actually quite quickly. All right, so now that's what the Monte Carlo simulation does. Let's look at some of the implications of those simulations. So for instance, what I'm showing you here is the no future launch case. This is a case that's run by most major space agencies. It's kind of one of the baseline cases. And what you can see here is we're not launching any more satellites. Starlink is at this altitude. Over time, as we stop launching, although the Starlinks will deorbit, and we would expect in an ideal world that there's nothing up there. We stop launching satellites, all of the space debris would come down. Turns out that there's space debris at high enough altitudes where they persist, and they're going to be up there for quite a bit of time, and they actually grow. So even if we stop launching today, we see at some altitudes there's going to be a growth of space debris over the scale of hundreds of years, for example. Now, if we model the future traffic and we look at, okay, this is not the no future launch case, but the dramatic traffic I showed on the first slide, and we've included here all of the major constellations that are planning launches. Some of them are actually being deployed currently, like the Starlink and Amazon one. We've removed some. There's been some filings that we've deemed they're not credible. So this is the most credible of the filings, not an exaggerated list. And you can see we've actually modeled how they're going to deploy. They're not going to just deploy instantly. There's going to be a gradual deployment. And if we model this, we see that the number of objects actually decreases. This is all objects pretty rapidly, all objects in this mega constellation. This includes debris objects, everything increases pretty rapidly. And you can compare that to the no future launch case that I showed earlier. The no future launch case is this one, all future traffic is that one. It's a dramatic difference. And you can see we're pushing really 10 to the 7. So this is something that the simulation is not possible with the other tools that I mentioned earlier. It's only possible with the capability that we have with MoCat. Some folks think that Starlink Gen 1 and Gen 2 are an issue. So Starlink Gen 2 is about 30,000 payloads that they're going to launch 30,000 satellites. They currently have 5,000. And that's a major concern. 30,000, is that sustainable? Now, in this scale, we're seeing that it doesn't create that much of a difference. The difference between Gen 1 and Gen 2 is really the number of satellites that are part of the constellation. But in reality, this big difference is coming from the higher altitudes. So the things that we do at high altitudes, they're less forgiving than things that we do at low altitudes. We've known that for a while. But what we haven't been able to do is simulate this really dense traffic and understand how bad it could potentially get if this traffic is realized. You could see that on the left, this is Starlink Gen 2. This is Starlink without Gen 2. Gen 2 has a lot of low, very low satellites. You can see this dark band is the Starlink Gen 2 below 400 kilometers. And on the left here, there isn't that low band. So what's going on there is that there's not much increase of space debris at these low altitudes because the atmosphere really cleanses the orbits. But you can see this banding that happens. That's due to the solar space weather, the solar cycle. So as we go through the solar cycle, when we're in low solar activity, the atmosphere is low, and we have more debris that's generated. And we go to high solar activity, the atmosphere puffs up. And in here, I'm showing you the no future launch case that I showed earlier. But what I like to do is just dive into this effect. So if we look at the FCC traffic model, we can see at these higher altitudes, there's this band of red debris that happens. So really that red picture I showed you earlier is a problematic activity at these high altitudes. And, where do we go with this? So one of the ways, and I'm wrapping up the talk now, is that we'd like to go with this is really have an evolutionary approach to managing this natural resource. So, unconstrained utilization is really what we had in the past, but in most natural resources, we've gone over an evolution from unconstrained utilization to scientific management. Finally, really good approach to managing common resources is adaptive governance and adaptive management, where we have these models that can model the environment and we can really adjust to what the economic demand is. So if folks want to launch in different orbits, we'd like models that can adjust instead of setting these really rigid requirements on where we can launch, how we could operate satellites. And we hope that our work is leading to that. So I think I'm running a little bit low on time, so I'm going to skip and just go to the conclusion slide here, which is, the problem today is we need to really transition from a qualitative to a quantitative discussion on space sustainability and transition to evidence-based policymaking. Currently, there's no shared definition of orbital capacity. I've presented some here in this presentation, but across the world in all the major space agencies, there's not one definition. And we really need to start agreeing on what do we mean by orbital capacity and space sustainability. And per mission guidelines, which is the current way of operating, is insufficient. We really need to look at the entire LEO environment and see, what the environment looks like. There are various modeling approaches that exist. A lot of them are closed source, so it's really hard to replicate, and this models the debate. Finally, there's fear that space sustainability can be weaponized as a regulatory market exclusion tool. If we really guide ourselves with basic physics and first principles, I think we could avoid that potential hazard of having sustainability really being used as a market exclusion tool. But in reality, sustainability is being used as a way for us to decide how we engineer systems to be more sustainable in low Earth orbit and use our resources more wisely. With that, I want to end just some concluding thoughts here, and then hopefully there's some time for questions. I see there's some questions here in the chat.
Definitely. Thank you very much, Richard. And we'll go definitely from the chat. And for those who don't know, you can enter your questions in your set, and you can upvote any questions that you would like to be answered. I'll just start off with a question from, let's see, I had it. It's completely different. From Robert, how important satellites become, how vulnerable are they to hacking, solar flares, or other natural problems? You mentioned some of them, but
Yeah, how vulnerable they are to hacking, solar flares. Yes, I think space security is not studied, cybersecurity is not studied as heavily. There are some colleagues of mine, I can think of a few that are studying it. It's not my area of research, but definitely they're very vulnerable, as vulnerable as other systems. So for example, their ground networks can be vulnerable to hacking. And that can really, create a risk if you hack a satellite and then you deliberately, destroy the constellation in some way. I think that's a major risk. There's been anti-satellite weaponry used, and actually a lot of the collision avoidance maneuvers that are happening right now in low Earth orbit are due to the Chinese ASAT test that happened a few years ago. And that ASAT test basically flung debris into higher altitudes. And so Starlink, the majority of the collision avoidance maneuvers that Starlink is doing is because of that. So I think a lot of these hazards are there. And then we just need norms where maybe we don't use, it's hard to do that, in an open conflict, but we shouldn't really destroy our environment in a conflict like that. But you're right that this is an open risk.
Joe Horton had a question. Anyone given thoughts to requiring satellites to be able to deorbit themselves when their useful lives are over? Recognize the odds, mass retro to the launch, but this seems that would go a long way to solving this.
So yeah, there are requirements on that. So NASA used to have this 25-year rule that all objects would either naturally deorbit or passively deorbit or actively deorbit within 25 years. And the FCC, which licenses a lot of these large satellite constellations, updated that rule to 5 years, from 25 to 5 years. And so the issue there is then, there's going to be cases where satellite fails. So that rule right now is kind of very rigid. But in reality, what we need is more or less like what percentage of satellites are you going to deorbit? Are you going to do that at a 95% rate that you're going to achieve that 5-year rule, or a 97% rate? And verify that operators are designing their systems in a redundant way where they actually can achieve that. And one mechanism to do that, which Starlink uses. So one of the things Starlink does is they launch into very low altitudes for their initial parking orbit. And they launch around like 350 kilometers, which is very dense atmosphere. And an object that fails at that altitude is going to deorbit within a week or so. And then once they do all of their checkout procedures, then they raise their altitude using Hall effect thrusters and electric propulsion to their final destination, which is around 550. Even at 550, if you fail, you're going to meet the 5-year requirement deorbiting rule. The challenge is in satellites that are going up to higher orbits. So if you go up to 800 kilometers, or let's say 900 kilometers, you could be up there for 100 years if you fail without a propulsive way of deorbiting. Now, some folks have proposed that we should have an industry of active debris removal, that if someone fails in that situation, can go up there and remove them. And I think all of those solutions are great. We just need to have a more robust conversation about that.
William says, how many collisions have been documented?
So there have been there's been one well-documented, which is the Radium Cosmos collisions, but there have been a few that are thought to be collisions. So there's failures and debris events. There's one in GEO that just happened recently. I feel like that was a few months ago. So there have been a few of these documented collisions. Now, debris on debris collisions is hard to know how many of those there have been. One thing that we have a lot that occur is explosions. So spent upper stage rocket bodies. I think the number that I've read in the literature is that there's one explosion a month. from these spent upper stage rocket bodies. Now, there's been some new guidelines that have come out that, you should pacify those rocket bodies, like, expend all the fuel, make sure that there's no pressurized things on that rocket body. There's also explosions that happen from satellites and their batteries exploding and things like that. But in terms of collisions, the number is still relatively low, but there's definitely been a few. And of course, there have been ASAT tests. Starlink, I don't think has seen a major collision event. They might have seen smaller debris events that have destroyed a satellite, but not a collision event that have generated thousands of pieces of debris, which is good. I think that's a good sign. The risk is if we have a lot of space traffic, we increase the probability of one of those collision events, and each one can generate actually thousands of debris. So the Chinese ASAT test was about 4,000 to 5,000 pieces of debris that were generated from that. So yeah, hopefully that answers the question.
Right. Robert Zimmerman was asking, are these spin stabilizing chains still used?
So these are like the fluid rings. I think maybe that's kind of what's being referred to here, like having a friction device to remove the rocket bodies that are spun up potentially. I don't know how much that's used nowadays. I know spin stabilized was used a lot more in the past than it is used now, spin stabilized satellites. So short answer, I think it's less, but don't quote me on that.
There's a couple of questions. I mean, considering we're in this era, how does this modeling theorizing comport with the current administration in DC, given the set of orbital shells considered full? Are Musk people going to accept your conclusions?
Actually, I think the folks that work at Starlink have mostly been fairly reasonable about some of these issues. So one of the work that we did is we figured out ways to like stack orbital shells. And essentially what you want to do there is like, let's say you have a limited orbital volume that you can occupy for satellites. We know that there's high economic regions in altitude that everyone wants to go to. How do you stack as many shells as possible? One of those regions is 590 kilometer altitude. As additionally, there's the 690 kilometer altitude region as well. Starlink and Amazon and China both want to operate very close to each other. So we came up with a method to basically use the space more efficiently. And it turns out that the Starlink folks, they adopted that and they're using it. Now, in terms of like, orbital capacity restrictions, I think overall, I think their approach is that they don't want any restrictions on orbital capacity, but I think over time, it's not going to be a unipolar world. China's going to be up there. They're going to have a lot of constellations. So we're going to want to figure out, okay, how do we operate more sustainably in those altitudes? And I think there's a lot of common sense ways that we can do that don't really affect the business case of some of these companies. And I think, at the end, a lot of these companies just want clarity from what international actors are going to do and clarity with what the US government's going to do. So I think overall, I think it is, being well received. But of course, yeah, I mean, I think if you leave it up to some companies, they don't want any change in their activity. But Starlink, on the other hand, has been pretty receptive to this.
Here's a funny one. I mean, the last question I'm going to go through is, when will we have space garbage trucks? From Hank, and then there's another one. How realistic is it to have garbage collection required?
Yeah, I know. I think it is realistic. That is realistic. So we have the Astroscale company. Their business case is just going up there, removing satellites from orbit. I think that is really realistic, especially if we have a way to incentivize them to do that. So for example, the FCC right now has a 5-year rule. We're not sure what the penalty is. So let's say they actually suggest what the penalty is going to be. Well, if someone says, okay, well, what we'll do to reduce our penalties, we're going to hire a company to go up there and remove our satellite. That could be a really good business case, especially if these orbits are valuable. If there's a satellite occupying an orbit that's valuable, you kind of would pay some money to clean that orbit up so that you can do what you need to do there.
Well, thank you, Rich, for a fascinating discussion and for sharing your insights on orbital carrying capacity and implications.
Thank you so much. Thank you for the invitation.
Wow. And once again, for all of you online, thank you all for being here today.
Thank you.
Yeah, deeply grateful. Thank you. Please enjoy the rest of your today. Thank you.